Let's hide the meeting controls. So good morning. Happy Monday. Seems like we have the few and the proud here. So thank you. Class participation is 5% of the grade. So I appreciate your dedication on this cold Monday morning. So today, our purpose is to talk about something called conditional probabilities. And it's a really important concept as it pertains to data science, because as we'll find, and we'll discuss this today, it's immensely useful for a broad array of applications, including the extraction of insights, particularly clustering as well as prediction. But before we begin, oh yes, and today we will also have some exercises. Hopefully we'll get to that. I budget for a certain amount of questions, and sometimes I hit, sometimes I miss with that time budget. And so the plan is to go over the material about conditional probabilities, and then hopefully spend the balance of that, maybe about 25 to 30 minutes. I'm estimating having you go through some exercises. And so what I'll do is stop the video and just go through the exercises where you all will have an opportunity to come to the board and explain a couple things. And it's your opportunity, put yourself out there, make the mistakes and stuff like that. But it's to the exercises are tuned, excuse me, to looking at complex events as well as going through those heuristics that we talked about concerning complex events and counting. All right. Any questions now? All right. I was mostly sick this weekend, so I'm still a little bit the remnants of what my daughter brought home. So I apologize ahead of time for that. Excuse me. All right, so before we begin, the usual administrative bits, the reading has not changed. And again, the deadline is there to help you with the pacing. This is a very accessible book, very easy, relatively easy to understand. And so it includes aspects on counting, conditional probability, and Bayes' rule, which is ultimately what our discussion on conditional probability is building towards. Okay. So when we last left off, excuse me, we talked about counting. And for that, we motivated it with two examples where you're making a selection. And the goal was to be able to count or enumerate the number of alternatives you have when you're forming a selection, i.e. picking a set of things from a slate from which you choose. And so we gave or started, excuse me, with two examples. One was a 3-on-3 football team. And in this case, we had a slate of 3, 4, 5, 7 players. And we were going to pick two groupings of 3 from these 7. And the main observation from this example was that when you make a choice to assemble your 3-on-3 team, each time you made a pick, the number of objects available for selection changed. It reduced by 1. And that selection didn't matter which particular player it was. What mattered is that once you pick that player, the player was no longer available for subsequent selection. Okay. The other example, excuse me, we gave was choosing our color palette for drawing. And with this, again, we assembled 2 palettes, and each palette in this example had 3 different crayons or colors. And the key takeaway from this example was that when you make a choice, you're just writing down what your selection was, but you're not removing from consideration that particular object that you selected from the slate of objects. And the former we called without replacement. And this example we called selection with replacement. Okay. Any questions to jar your memory? So then we also moved our focus, our attention. Why doesn't this work? Nope. No. Uh, oh, that's weird. Ran out of batteries. I'll just use the keyboard. The other thing, then we focused our attention to this idea of duplicates. And we motivated that using a family example. And the takeaway here was whether you treat the order of arrival for the selection of objects when you're forming your groupings, or you do not consider the order of arrival. And so if you do not consider the order of arrival, approach one said there were three different possibilities for having two children. If you consider the order of arrival for your selection of objects from some slate of objects, then having a girl first followed by a boy and a boy first followed by a girl in birth order, they were treated as different objects. And so these considerations are important because it impacts how you enumerate or count all of the possible outcomes when you're trying to list them out. Oftentimes you list them out as selections from a slate of selections from a slate of objects. Any questions? Make sense? Are your memories? So we started out then mathematically with permutation without replacement. And in this case, we have a slate of n, little n, many objects. So that's like the roster starting with 7 soccer players. And we want to assemble a group of them of size k. And so here in our expression, we have k many terms. The first pick has n choices because you have the full slate of objects. And each subsequent pick, the number of possibilities or choices for each subsequent pick reduces by 1. And so there was a question before about why is that last pick n minus k plus 1? And the thing to remember is what we're concerned about is the number of alternatives you have, not the number you're left with after you make that pick, right? That's really important to remember. And so this sequence of multiplications, this chain of products of the number of options together on each pick represent the number of ways that you can pick these k many objects from a slate of n. Now, in this case, we count the orderings, the different orderings, as being different selections, right? This is without replacement. We remove from consideration. But here, we're making a so-called distinguished selection. And so if we pick the first object and the second object, that's different from picking the second object than the first object. Okay, any questions? Does that make sense? Okay. And so if we were to write this compactly, we would write it as n factorial upon quantity n minus k factorial, where factorial for an integer is just the product of terms each time decrementing by 1. And so if we had 5 factorial, it would be 5 times 4 times 3 times 2 times 1. Okay. Any questions? Does that make sense? All right. And we can get to our original expression that we had up top with the k many terms from our compact notation by just expanding what factorial means. And we're able to cancel a copy of n minus k factorial in the numerator with n minus k quantity factorial in the denominator. Okay. Any questions? No? And so we then turned our attention to indistinguishable selection. In the case of indistinguishable selection, if we pick, say, object 1, then object 2, that's not considered different from picking object 2, then picking object 1. And so in that case, we have the same expression. If we look at the expansion, we have n factorial. Let me choose blue pen color. We have n factorial in the numerator, and we have quantity n minus k factorial in the denominator. But we introduce the second term in the denominator, that k factorial. And what this k factorial is doing is it's reducing or accounting for the number of different orderings of the k many objects that you select. And so suppose you had, in the case of a soccer team, let's say you had a slate of 7 players, and you're going to try to select 3 of them. Suppose you have these 7 players, player 1, player 2, player 3, ... player 7. Now, of course, when you select 3 of them, let's say, let's draw in player 4. If we selected player 2, then 3, then 4, we could select them as 2, player 2, player 3, player 4. We could select player 3 first, and player 2 first, player 4. We could select player 4, player 3, player 2. In this case, for the indistinguishable selection, this indistinguishable arrangement, each one of these orderings, in this case of these three players, and that's not exhaustive, is treated as the same thing. And so if we have k many objects that we're selecting out of that slate of n, well, for that k many objects, k many, you have k choices for the first pick, k minus one choices for the second pick, two for the second to last, and one for the last. And that's exactly k factorial. And so here in the denominator, when we make it an indistinguishable selection, we have to account for all of the k factorially many orderings that we can have for those k many objects that we're picking from that slate of n. Okay. Any questions? Does that make sense? Jar your memories? I think I forgot to explain that part last time. We release the pen. Oops. Uh-oh. Let me do this. Hide the meeting controls. Okay. Oh. There we go. Okay. So now that first set of selections, that was without replacement. We also need to account for this idea of indistinguishable selection of arrangements with replacement. And for that, we use that combination, that selection without replacement, as the mechanism for calculating this. And for that, we use the balls and bins abstraction, where each one of the bins is represented by a vertical bar. You can think of it as a divider. And each one of the selections you make is treated as the toss of a ball. And so whichever slot that ball lands in, that corresponds to a pick of that particular object. And so we said we needed n minus 1 bars in order to represent slots for n objects. And each one of these balls, there are k many balls, because we're trying to pick k many objects from among k many selections from among that slate of n objects. And so with this, if there's more than one ball, excuse me, in a slot, that represents that that particular object was picked more than once. And so if we have these n minus 1 bars and these k many balls, all of the possible ways that we can pick with replacement is nothing more than the set of arrangements that we can have for these k plus n minus 1 objects. And so with that, if we have k plus n minus 1 objects, we have k plus, oops, this is one of those days. We have k plus n minus 1 choices for the first arrangement, for the first pick, and then we have k plus n minus 2 for the next one, and then we have k plus n minus 3, and eventually we get to 2 and then 1. And so with all of these arrangements, that's the permutation or the set of all of the arrangements that we can have for these k plus n minus 1 many objects. And so with this, of course, we want it to be indistinguishable. So we have to discount for the fact that when we have these balls, for example, these three balls, we don't care if it's ball 1 followed by ball 2 followed by ball 3, or if it's ball 2 followed by ball 1 followed by ball 3. It doesn't matter what the particular ball is. And because we have k many of them, we need to discount this particular expression, k plus n minus 1 factorial, by k factorial, because we don't care about which ball it is, the ordering of those k many balls. Likewise, we have n minus 1 of these bars, these slots, these dividers as they were, as we talked about them. And it doesn't matter which divider is which, right? We could have divider 1, divider 2, divider 3, etc. Or we could have divider 3, divider 2, divider 1. It doesn't matter what the ordering of those n minus 1 dividers are. And so we take our expression k plus n minus 1 factorial, and we divide by the number of orderings of these bars. And then we also divide by the k factorially many orderings of the balls. And this is our final expression. Now, of course, this is the expression, but we can get to this expression using our combination. And here, when we originally talked about combination, we said n choose k. Here we're substituting for our n term with this expression, and we're substituting for a k term with that expression. Does that make sense? Any questions? Jar your memories from Friday? Yeah? Okay. All right. So let's turn our attention to what I'll call at this juncture filtering probabilities. And this is really just an eye towards how you might implement it in something like Python or any mathematical modeling language. And so we talked about random variables. And for our discussion of random variables, we said a random variable is some measurement or function over what we're calling a raw observation or an object. And this outcome of our measurement is uncertain, hence the random part for random variable. And with that, well, we talked about outcomes that already happen. We run a trial, we make an observation, we get a raw event, and then we measure something over that raw event, namely our random variable. Now, one of the things that are immensely useful for certain systems is the consideration of how new trials might impact your probabilities. Because if you have a new trial and something else happens, some observable is observed, or some outcome is observed, that's going to change what your thought is or your current running idea about what the probability is. Okay. The other part that can be very useful with probabilities in general is something called scenario testing. You can sort of pretend that you saw a particular outcome, and based on what you're imagining you saw as a future outcome for a future trial, you can evaluate what that consequence is in terms of the probability. Because with new information, the probability certainly changes. So let's motivate all this with an example. And let's imagine we had a random variable that we're calling C. And let C stand for color, and it measures the number of tennis balls of a given color picked from some container or bin. You can imagine it's opaque and you're blindfolded. So you can't see the color of the ball. But I'm going to show you what the bin looks like. And we have some number of balls. We have 12 balls, and some of them, 5 of them, are colored green. Now, going back to first principles, we said the probability that a random variable takes on a value is the number of favorable over the total. And so let's ask you, if you were to look at the probability that this measure of color is an outcome yellow, how would you calculate this, right? What's the total number? Not a trick question. Get you warmed up in the morning. 12. Yes, it's 12. Okay. So our denominator is 12. And how many of them are yellow? Not a trick question. It's just 7. Okay. So let's just express that ratio. So if 7 of them are yellow, how many are green? If it's a total of 12. 5, right? So it's 5. So again, we just follow the recipe, the total number of the number of favorable, what you're looking for, over the total. So we have 7/12 probability that this random variable C takes on value yellow, and we have 5/12 that this random variable C takes on green. You'll also notice if I add these two together, all the possible outcomes, yellow and green, add together the probabilities, it sums to 1, right? That's a requirement of being a probability. Probability over your universe of consideration must always equal 1 if you sum them together. All right, any questions? No? All right. No? All right. So let's make it a little bit more interesting. So here, we're going to increase the number of balls to 20. And we're going to make it a little bit more interesting. We're going to store our tennis balls in some bins. And depending on which bin it comes from, we're going to get a big Sharpie marker. And we're going to write the bin number to which that ball belongs. Um, so now with this, I'm going to blindfold you and we're going to introduce a new random variable, B, and B is going to stand for the bin number attribute associated with each one of these tennis ball objects. And so here, if we were to ask, and I'll ask you, what's the probability that if you were blindfolded, I took all of these bins and I emptied them into a sack, and the sack was opaque, you couldn't see what's inside of it, and I blindfolded you, and you were to pick out a ball, what's the probability that your selection would be a ball with a bin number written on it, where B equals 2? All right, so let's go through the mechanics. Again, we take the total number of items in the denominator, and we take the number of objects you desire in the numerator. So who wants to take a shot at it? It's 10 over 20, yes. And so that 10 over 20, we can express as a proportion, 0.5. So it's a 50% probability that you're going to pick a ball that originated from bin number 2. Okay, so let's add 2 attributes. Now we're going to bring back the color. So we're going to have some green tennis balls, and we're going to also have bin numbers written on each of the tennis balls. And so once again, now instead of 1 attribute that we're measuring, we have available to us 2 attributes that we can measure. And so in this case, let's go back to color. And again, we're going to take all of the balls in all of the bins, and we're going to empty them into an opaque sack. And I'm going to blindfold you, and you're going to pick a ball out of that sack. So in this case, if we had our random variable C measuring color, what would be the probability that you picked a ball where that color is equal to green? Again, we follow the first principles. The total number of items has not changed, but what we desire, we filter through that has changed. So what would that be? So we'd have what? 4 out of, I'm sorry, out of 20, 4 out of 20. Thank you. So we'd have 4 upon 20, which is 1/5 or 0.2 probability. Okay. So what if we're only concerned about some of the bins, but not all of the bins? And so imagine, again, somebody whispered in your ear. You say, hey, Wholeness didn't empty all the bins into that sack. I only emptied some of the bins, not all of the bins. Now, certainly that information is going to change your probability. And how it changes your probability is by changing the so-called universe of consideration. And I'll explain a little bit more about what I mean by that. But this idea of changing the universe of consideration gets to the point of probability with filtering. And so this conditional probability, if we were to list it out syntactically, here we have the probability of some variable, variable 1 takes on a value, and you have this vertical bar, the given bar, the condition bar, variable 2 takes on some other value. And so how you'd pronounce it is the probability that variable 1 is some value given that variable 2 is some other value. And so what this condition does, variable 2 equals other value, you can imagine if you were implementing it, you would iterate through all of the objects that you have in your universe, and you'd set aside those objects for which variable 2 is equal to other value, for which that is true. And so what that ends up doing is changing what your universe is. It's no longer everything you had. It's only those objects that you set aside that pass this litmus test of sorts, that variable 2, that condition or that measurement is equal to a specific value. And so you filter out or set aside objects for which variable 2 is that specific value. And then for what's left, everything that passes, you're going to compute the number of favorables, the proportion of those objects for which variable 1 is some value. And so the numerator has not changed, the number of favorable outcomes, but the denominator has. Our universe of consideration is no longer all of the possible outcomes. Okay? Any questions? Does that make sense? Yeah. All right. And so with this, go back to our example. Suppose somebody whispered in your ear when you're blindfolded, hey, Wholeness only dumped the contents of bin number 3 into that opaque sack. So then how we would write this would say, what's the probability that the color is green given that the bin number was only those from bin 3? Okay, so who wants to take a crack at it? So what do? We say, okay, let's go through all of our objects. Is this ball bin 3? Nope, 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 nope. Nothing in here, nothing over there. So you're only considering those objects for which that attribute B is equal to 3, bin number 3. Okay, all right. So now, again, knowing that the total items is changing, what is our total items now if we're only considering those objects for which our measurement B is equal to 3? How many do we have? 2 out of 5, yes. And so 5 is our denominator. Our total has changed because we're only considering objects for which the bin number is 3. And then we look at green, it's 2 out of 5, which is 0.4. And so if we look at this, we notice something. Before, if we didn't have that piece of information that bin equals 3, our probability was 0.2, right? It was 204 over 20. Now, with this extra information, our probability has increased. The presence of this information changes what our probability is. And not only can we do this with something we observe, we could imagine, what if the bin number were 4? What if the bin number were 1? What if the bin number were 2? So now we can scenario test and evaluate alternatives without necessarily having observed them. Okay. Any questions? Does that make sense? Yeah. And so this idea of conditional probability is a framework that allows us to traffic in this idea of what happens when new information is available. And so probabilities, as we've discussed, are certainly based on observation, and new information can change a probability. And so it's useful to be able to evaluate probabilities with this concept of in light of new information. What happens if the following is observed? Now, this is what a conditional probability is. More compactly, we say the probability of event E given observation of event A, where event A is, in both cases, E and A, the outcome of random variables. Okay. Any questions? Does that make sense? Yeah. All right. And so to ground this out, imagine it's a warming spring day and you're going out onto the quad. Spring is upon us and nature is waking back up again. You see the flowers and the buds on the trees beginning to bloom. The squirrels are frolicking around. And all of a sudden, this Friday afternoon, or right after class, a meteor strikes the quad. Now, of course, this might seem like an unusual occurrence, but you made this observation. And every single Friday afternoon, as soon as you step outside of Jonas Clark, you look towards the skies and boom, there's a meteor. Okay. So let's imagine then each week this happens, and you can think of your sample space, omega, as either having a meteor strike on that day or it's clear. Okay. Now, of course, you might want to know, because it's useful to evaluate, what is the probability that there's going to be a meteor strike in the afternoon on your Friday classes? Now, let's imagine then each week, for week 1 of the semester, week 2, 3, 4, all the way up to week 9, like clockwork, every single Friday afternoon, as soon as you set foot outside Jonas Clark, a meteor strikes. Now, of course, in this case, our observations tell us it happens reliably. And now 9 times out of 9 weeks, every Friday afternoon, this observation occurred. Okay. So in that case, the probability of your meteor strike on a Friday afternoon after class on the quad is going to be 100% or 1.0. Now, of course, in your experience, that seems nonsensical, right? Because you've had enough examples that on a Friday afternoon in the spring, a meteor is not striking on the quad, right? Watch it happen like this spring and be like, how do you know? Now, let's imagine all of a sudden, week 10, you pensively set foot out onto the quad on Friday afternoon after class, and it's clear. There's no meteor strike. Now, of course, with that 10th measurement, now your probability is going to change. Before it was 100%, and now it's 10% clear and 90% meteor strike. And so this idea of in light of new information is immensely useful for evaluating the consequence of new information without necessarily having observed that new information as an example. Okay. Any questions? Does that make sense? Yeah. All right. And so this idea of conditional probability gets to a class of approaches called Bayesian statistics. It's somebody's last name. And it's very useful for making predictions based on a sequence of historical observations. If you've ever used like your text messaging and you have this autocorrect and you start typing something and it suggests like three different words that you might be typing next, that's an example of a conditional probability. Essentially, it's looking at word sequences and it's predicting or evaluating the top three probabilities of the next word that you're going to type, given a sequence of previous words that you've typed. And so you can use this idea of conditional probabilities to do prediction. And then based on the highest probability, you say, okay, that is my most quote unquote reasonable choice based on my historical observations. It's very useful, this idea of conditional probabilities also in weather prediction. If you've ever, during a hurricane, you watch the news and you see these hurricane tracks and they draw sort of this graph, if here's Florida, because it's usually Florida, and this is, it's Texas, Gulf of Mexico, Louisiana, Alabama, Florida here, and they draw something that looks like this, right? And you have all these lines that, move out in various directions. Well, among other things, they're using differential equations, but they're also using probabilities. And these probabilities talk about the vector or the direction in which this track will travel. And they're sort of iterating over the geography, and they're getting these lines that proceed outwards. And so that's useful, weather forecasting for things like hurricane tracks, but also just looking at the weather condition itself, the previous weather, given the previous weather, what's the probability, for example, that you're going to get rain the next day? Okay. Lastly, and this is not the only example, in robotics, it's immensely useful for using sensors to do what's called localization, try to figure out where you are in the world from your sensor measurements, something called Monte Carlo localization, or no, not really quite SLAM, but SLAM is an add-on to that. So you have a set of measurements, and through your sensors, you're looking for something called stable landmarks. Those are features in the environment, could be visual, could be other types of measurements like range measurements. Features that don't change very much are your so-called landmarks. And so then you have a bunch of previous locations that you encounter as you move through the world as a robot mechanism, mobility platform, and you're trying to evaluate what is the probability that you're in a particular or certain location given a sequence of previous locations. Because with this navigation or localization problem, you know that you're moving a certain amount, and this movement of a certain amount from one location is predictive of what that next location is. And so you build up enough of these examples, these random variables, samples over objects, and you can build these conditional probabilities, and they're immensely useful to allow you, based on your sensors, to calculate where you are in the world. Okay. Any questions about this? Does that make sense? And so this framework of conditional probabilities is immensely useful. Now, I sort of wasn't being entirely truthful when I talked about what a probability is. And in the statistics community, there are these two kind of warring factions that have different philosophy about what a probability means. Now, what we've been talking about when we kind of cutely called it "When Can I See You Again?" Is a so-called frequentist tradition of probabilities. And the frequentists believe that a probability is a proportion that represents the ratio of the number of particular outcomes that arise given an infinite or a large number of trials. And so they believe that a probability is a so-called repeatable objective process. And the seminal publication on that is by John Venn, the same John Venn who created the Venn diagram. And it's always an interesting thing to go back and look at the original contributions divorced of all the applications. And I fully encourage you to do that if you have the time, because it really grounds out what the intent was for these particular tools. Now, the other interpretation of a probability is a so-called Bayesian interpretation. And the Bayesians believe that a probability is this idea of a degree of belief. How much do you believe that something's going to happen? If your belief is stronger, it's closer to 100%. If your belief is less strong, it's going to be closer to zero. And with this, the idea is that now you can start to talk about these alternative futures that you don't necessarily observe. And, in full disclosure, in my graduate department when at UMass, when I got my PhD, they were more of a Bayesian computer science department. So I'll acknowledge that. But if you go to any statistics department, you're going to have these two groups. And I'm fairly pragmatic. They're both right and they're both wrong, right? But nonetheless, thinking of probabilities in different ways, this idea of a conditional probability is part of the Bayesian framework for what a probability is defined as. And Bayes was the mathematician, really was a monk and philosopher who created this framework. Okay, any questions? No? All right. So conditional probability. We say the probability of A given B, and A can be a single random variable, or it can be the conjunction, the combining, the anding of more than one random variable. And so here, while I say probability of variable A given variable B, it doesn't have to be just a single random variable on the probability side, the left side of the condition bar, or the condition part, the right side of the condition bar. Okay. Any questions? Does that make sense? And so let's go back to where we started. And I know the colors are kind of reversed here. We have our sample space omega that represents all of the possible outcomes, our so-called universe of consideration. And carved out of that sample space omega, we have our event A. So it's some collection carved out of what is possible. And so we said, if we evaluate the probability of this event we're calling A, it's the number of outcomes in A divided by the number of outcomes of our universe sample space omega. And so conditional probability, it scopes it down, and we'll show how we get to this. The probability of A given B is the following proportion. It's the probability of A and B, so the co-occurrence of those two events being true at the same time, divided by the probability of B. And so here in the Venn diagram, we have two events, A, and we have event B, and it's on purpose that they're overlapping. That region in the middle here, where A overlaps B, those are the objects carved out of our universe of consideration that are common to both A and B. They're both true. It's at the so-called intersection or the overlap region of A and event B. Sometimes you'll see it just called A and B. Now, when you look at the literature in statistics, this and is often written as A, comma, B. Why do they leave out the and? Because it's a lot easier to write a comma than the and symbol, or conjunction as it's called. And what that means is that event A and B are true at the same time. And so if we had, for example, on rolling the die, and we have an event A is equal to, for example, 1, 2, 3, 4, and event B is equal to, let's say 3, 4, 5, 6, the intersection of event A and event B is going to be 3, 4. They're both true at the same time. So only those objects, 3 and 4, hold true when A and B are true, for A and B to be true at the same time. Does that make sense? Any questions? No? All right. So this probability of B part, that hasn't changed. In that case, it's the number of outcomes in B divided by the total number of outcomes in sample space omega. And so what this does is it takes our universe of consideration and it shifts it down, not from omega, but only to that portion of omega where B is true, because we're given that B is true. That's the information that we have. And if we were to kind of expand this expression, we say the probability of A and B, going by our definition of probability, we have in the numerator, we have the number of outcomes where A and B are true, divided by the cardinality of our sample space omega. And then the denominator, we have the number of outcomes of B divided by our sample space omega, the cardinality. Well, in this expression, the cardinality of sample space omega, that cancels, and we get number of outcomes for that overlap region, A and B, over the number of outcomes where B is true. And so essentially what that condition given B is doing, it's changing our sample space omega, our universe of consideration, and it's shrinking it down to that portion just exclusive to where B is true. And so here, our new denominator in our expression is this B region, and the part for which we're computing that probability for is this overlap region. So it's the number of objects our preferred overlap region divided by the number of objects in B. Does that make sense? Any questions about this? And so relating back to the tennis balls and bins example, how you would compute this is you'd iterate over your sample space omega, you set aside those objects for which your condition B is true, and then you compute your favorables and divide by the total number contained in B. Does that make sense? Any questions? No? All right. And so the number of favorable outcomes, number over the number of total outcomes, that scheme does not change, but it's our denominator that changes from sample space omega to that portion of omega where condition B is true. Okay. And so that's why we saw that when we have new information, our probability increases. And the probability tends to increase, not always, but it tends to increase when you shrink down your universe of consideration. If the denominator gets smaller, the proportion is going to get bigger. Okay. Any questions? No? All right. Okay, so here's an example. And let me ask you, suppose you have a die, go with the straight one and then have some variations. What's the probability of rolling a 2 on a standard die? That's a fair die, right? The 1/6. And so, absolutely, yes. And so you take our favorables, you iterate through how many outcomes are 2, one of them. And you take the total, the cardinality of a sample space, it's 6, 1 upon 6. And so I always want you to go back to the rules, right? Okay, so let's change it a little bit. Let's have a little bit of information and imagine it was a loaded die. And for this weird loaded die, just imagine that the outcome was always even, right? What's the probability of rolling a 2 if the outcome will always be an even number on the die? Anybody? No? It's 1/3. And so here, with our sample space, our universe of consideration, limited to the evens, now instead of the full set 1 through 6, it's now our universe is now 2, 4, 6, which is the name we're given, evens. We name it evens. So now, given that our cardinality is for our new universe of consideration is now 3, we iterate through how many are favorable, how many equal to one of them. So 1 over 3, 1/3. Okay. And again, having that information, it changes our probability. We go from 1/6 to 1/3. Okay. Any questions? Always go back to first principles. So let's make it a little bit more complex. We're going to have a standard deck of cards. And so for those who don't know cards, you have I call it a jacket. It's like a value, and it goes 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have Jack, Queen, King, and Ace. And so depending on the card, if it's in the direction towards Ace, the card has more value. If it's in the direction towards 2, the card has less value. Now, there's also a suit, and the suit can be one of 4 things: spades, hearts, diamonds, and clubs. And so each card, you have 13 cards, and each of those 13 cards has one of these suits. So you have a total of 13 times 4, which is 52 cards. And so one question you might ask, what is the probability if you have a full deck of cards and someone deals to you a card? What is the probability, excuse me, that that card is a king? Okay. So again, we say, okay, well, my sample space omega, the cardinality is equal to 52. And if I look at my kings, I have a king of spades. I have a king of hearts. Let me just do that. That's not really notation. I have a king of diamonds, and I have a king of, I can never do it. It looks like a clover of clubs. I think that's clubs. And a spade is, well, I'll just say S for spade. I can't draw. And so I have, if I iterate through my universe, I have 4 cards that are kings in terms of their value, the type of the card. And so I take 4 upon 52. It's the number of favorables divided by the cardinality of the sample space, which is 1/13. Okay. Any questions? No? So let's take a look now at a conditional probability. You're playing cards, and you start with a full deck, and you see the dealer deal out a king, and it doesn't matter what the jacket is, whether it's spades, heart, diamond, or club, but you see the dealer deal out a jack to somebody, a queen to somebody, and a king to somebody. Now, a question you might ask is, what is the probability after seeing that, given that a jack, queen, and king have been dealt? What's the probability of getting a king? Again, now in this case, you have to evaluate the impact of what you're given. If we start out with our sample space, cardinality is equal to 52. Well, when the first card is dealt, it's a jack. Okay, we now have 51 cards. If the second card is dealt, we now have 50 cards left. Once the third card is dealt, third card, this brings us down to a cardinality of 49 cards. Now, out of those 49 cards, well, we know starting out, it had 4 kings. It had the king of spades, the king of hearts, the king of diamonds, excuse me, and the king of clubs. Now, if we dealt out one of those cards given was a king, we only have 3 kings available because the dealer has dealt one out. So if that's the case, you have 3 kings available. Our sample space, our new sample space, omega new, has a cardinality of size 49. And we have a total of 3 kings. If you were to iterate through for your favorables, you're going to have 3 kings over our sample space, omega nu, has a size of 49. And so again, when we are given information, we need to do a filtering or setting aside of our original universe of consideration, shaping it down to match the condition that's given. Okay, any questions? Does that make sense? And so please resist we're going to have a written assignment. That's why I'm going over this. Please resist the temptation to want to jump in and just solve it. go back to the first principles, especially these rules about selection, right? It's really, really important to just kind of hold on for a moment, evaluate the problem, gather the information you need for the problem, and apply these rules. It really is prescriptive. Okay. All right. Any questions? No? No questions? Make sense? Yeah. All right. And so let's go to some exercises. And I'm hoping to have all of you do the talking and not me. And so I have three problems here. And I'm going to turn off the video because it doesn't make sense to, have video for this portion. The important part is to get everybody thinking and reasoning through these problems, right? And these are selection problems. So we'll start out. Let me just stop the recording. Um, let's see. Why is the pen's not releasing? So stop the recording.